Hello, my name is John Olafenwa, and I'm going to be talking about reinforcement learning on large language models. In this video, my goal is to really go deep into some of the foundational concepts behind reinforcement learning, which is really the technique that has really driven agents to like their core capabilities today, and really um, giving LLMs this kind of superpowers across software engineering, mathematics, and like a wide range of fields. So let's just dive right into it, and this should be like quite an interesting video. Um, if you think about the in recent times, just looking at like Twitter, almost every day you see there is a new, like maybe 8-year-old conjecture that's disproved, or a new conjecture that is proven, and this happens across the labs, right? We had like the Kubian conjecture from like that's like this that was disproved by Fable 5, Matropic, and then we had the unit distance problem, as well as like the non-sophic groups, and this is like really incredible. And at the core of this is the power of reinforcement learning, which has like powered like previous breakthroughs like AlphaGo, AlphaFold. And I'm going to really talk in this video about like some of the maths, especially coming from pre-training, SFT, and like going all the way to like RL, and like how does this shape up? How does this like connect to each other? And how does like LLMs really learn from data? How do they learn from different tasks? How do they learn from like different kind of like rewards we give them, and all the way to like leading up to this? Of course, there are like so many incredible advances that underlie all of these breakthroughs, but I'm going to like just talk about the foundational concepts. An LLM ultimately can be seen as like a policy, speaking from like a enforcement learning perspective. It's like a policy that is sampling like actions. And those actions are typically in tokens, right? And so an example is if you take something like how many planets are in the solar system, and this represents like a single state, right? And you feed this into an LLM, it tells you, it maybe starts generating like output, and it says there, and you append that to back to the context. This becomes another state, and you continue like doing this until you have like a full response. There are 8 planets in the solar system, and so at each point you have like a state that consists of like all the history and like what the model has generated so far. And the model can generate an action, which is basically generates a token, and that token will be like one out of like several thousands of tokens it could generate at each step. So a typical LLM can have like a vocabulary size of like maybe 200K, and so that means at each step it actually could generate is generating one out of 200,000 possible actions. And this is like one of the things that makes LLMs like really interesting, and why we kind of need like pre-training before the RL can work. Because if you think about it, really at every single step here of this, so this is like what, like 8 steps, right? At this single step, the LLM is generating as like possibly like 200,000. Let's imagine it has a vocabulary set of 200,000 tokens. It has like 200,000 tokens to pick from, right? And over like 8, that is basically like 200,000 raised to power like 8 different possible actions, or different possible ways that this sequence could exist, which is like incredible, right? It's a pretty large number. And if you think about that, that's kind of like why the action space for an LLM is extremely large. And so, which is why we kind of need some sort of like word knowledge, like which comes through pre-training. And without that, you can't just start initialize an LLM from scratch and really expect it to use reinforcement learning to learn from scratch, and giving like such an arbitrarily large action space. And so this is one of the reasons why we are going to like really start this from pre-training and like talk all the way to RL. So pre-training is what really gives an LLM the world model, and helps it kind of like understand like how exactly the reward data is distributed. So if you think about what typically happens in pre-training, you have tens of trillions of like data, from books to code to research papers, all of this. And bring all of this together, tokenize it, turn it to like a very extremely large like pre-training corpus. And what you ultimately do is you pick like a single like maybe at the top you have like the input says, oh, the sum of 5 and 2 is, and you want to predict the labels below given the what's at the top, right? So for example, given the sum you want to predict of, given the sum of 5 you want to predict and, given the sum of 5 and you want to predict 2, given the sum of 5 and 2 is, you want to predict like 7. So basically it's just like taking this top and predicting what's below. Like you take a prior context and you want to predict what comes next to it. I mean, one way of like looking at it is you're reading a book and then you want to predict what happens next in the book. Like you could think about this in that way, and it's just like really like giving the past what happens next. And one of the interesting things is like if you think about an LLM, we really know that LLM is a good model when it contains basically the same information as it is trained on, which in this case really means um like if you ask the model a question, right, it gives you like similar like output as you would have gotten from the data. So for example, let's imagine we have this Wikipedia article about the United Kingdom, which is where I live, and you have like this kind of brief history of the UK. And the interesting thing is, if you ask an LLM the question, for example, a context like you feed it the capital and largest city of England and UK is. So if you look here somewhere here, we actually have that text because I actually picked it from here. Okay, that's interesting. So yes, the capital and largest city of England and UK is. We know from data it means London. So what we want is after our LLM is trained on this data, we want if we pass this context, what it should sample, the token it should predict as the highest out of like maybe 200,000 possible tokens it could predict should be London, right? And so that means if we pass this context, we get London. Same thing, uh, most of Ireland seceded from the UK in 1922. And from this, you can already see how we are basically learning things like the capital of England, right? And like when did Ireland secede from the UK? So what then typically happens is after you train your model, and then you go to your chatbot and you ask, oh, what's the capital of England, right? Uh, the LLM is able to tell you London, right? Simply because it's done this like like lots of data. And when you ask, oh, when did Ireland secede from the UK? Then your model is able to tell you 1922. And so this is really the idea, is just kind of approximating the distribution on which it's trained on. And this happens like over extremely large data, which gives models like a lot of world knowledge. And training an LLM really means you're minimizing the difference between the real data distribution and the distribution learned by the LLM, which corresponds to like minimizing the KL divergence between the data distribution and the model's distribution. So what so in a perfectly like trained model, right? What you typically have is like given some finite data, this scale divergence should like tend to zero, but it will never be zero because the real world like data, like it doesn't. It's going to always be like there's always going to be some amount, some scale divergence, right? Between like your data uh and your model. There's going to be some number. It will never be exactly like zero, right? Because but it will always like tend towards zero if your optimization is good. And to really understand what goes on in here in the scale divergence, we have to really consider one concept called information, right? So we talked about here about the model containing the same information as data is trained on, but we really need like a mathematical way to talk about like information and to like measure it, like measure what's the information in this piece of data, and like what's the information in that piece of data. How do you know if the information is different between these two pieces of data? It's not just something we can talk about. We need to actually like we have a means of like measuring that and defining that mathematically in order to like train models to like be really good. Now that's pre-training or reinforcement learning or other forms of like optimization that we do. Um, and let's take a step back and just think about something that is like not an LLM. Let's think about a book, right? A book on algorithms that contain like about 20 algorithms. You already know like 15 of them in your head, like you're really good at this. But there are like five algorithms in there that's like new to you, right? So in reality, the information content of that book we can then say it's just those five algorithms, right? Because those are the only things that you didn't know. That's like the uncertainty that you had before you read the book, and the information that you got from the book is those five algorithms, right? So that's the we can then say the information content of that book is basically like those five algorithms. If you think about something else, think about like someone told you on Monday that they're going to send you an e-meeting invite. It's going to be at like 3 p.m. or 5 p.m. And so you don't know, right? So there are two possible choices. It could be 3 p.m. or 5 p.m. And so you kind of like having this uncertainty. And information is like can be really defined as like what is that like uncertainty, right? So which is like basically one bit of uncertainty, like one binary choice. uh and so when maybe on Tuesday someone told you, oh yeah, the meeting is going to go by 3 p.m., you gain one bit of information, like one out of two choices, right? And um at that point your uncertainty goes to zero, right? So the information content of that of on Monday of like the of what the person told you 3 p.m., 5 p.m. is like two choices. It's kind of one bit. If you take a look at something like let's think about a guessing game, right? So let's think in this case about the World Cup, right? So an LLM learns by like choosing among possible answers, right? Like we have like different tokens. Which token should I choose? Which answer should I give this person? Which tool should I call? And so let's go back and think about the World Cup, which ended not too long ago. So the World Cup was ultimately about answering the question. The World Cup winner is in this at the final, like on the day of the final, right? You had like Spain or Argentina as the winner. So we needed just one single round of decision to like resolve that ambiguity. And so there was two possible outcomes, and we had just one decision round. And so we get like one bit of information after the winner. I'm going to really explain very shortly why all of this connects to pre-training and like what's common between these choices, these different like examples I'm showing. But just like look at a few more. Right. So let's think about like the World Cup round of eight. We had eight teams, and at that round we needed like three different rounds to determine the winner, right? Which is like first round we go from eight teams to four teams, second round from four teams to two teams, and final round from two teams to the winner. Right. So we needed three rounds of information, which is basically like think about it as like three bits, or to really identify like the winner from the eight teams. Another interesting thing is thinking about sorting searching through a sorted list, right? So if you have a sorted list, like 1 to 16, you need basically a depth of 4 to be able to go from the beginning to any single item, right? So you go in here or you go in here, you have like till 4 levels out of 16 items. So you need 4 rounds of like decisions, like go through get to any item. And this is this is actually very interesting because across all of these choices, like there is a simple formula you can actually use to decide the information content. Where the information content in this case is like the number of like binary decisions that you need to make to like get to the outcome you want. So at World Cup final, we have two choices. If you take the log to base two, yeah, base two giving us binary choice, right? If you take the log to base two of the two teams, right? We have two teams, two choices, you get one bit. If you take the log to base two of eight, you get 3 bits, right? So which corresponds to the 3 rounds of decision we have to make. And in the binary search, worst case scenario to like get to any item, you have log 2 of 16 gives you 4 bits. So if you looking at this across all of these examples, right? You can use that single formula, I equals log 2 of n, where n is the number of choices, and even this holds true when like all the choices are equally likely. So information can therefore be measured and defined as like the number of choices you need to like determine an outcome, right? And this can be measured as log 2 of the total number of choices available, especially under a uniform distribution. So henceforth, we define information with this simple formula. Log 2 of n gives you the information content of any set of choices that you are faced with. And this will make sense if you think about like logarithms and exponentials more, which is something we're going to like use throughout. And you have this you have exponentials in the form of a base raised to power an exponent. So for example, 2 raised to power 3, this gives you like 2 times 2 times 2, which is 3 times. That is how many times do you multiply 2 until you get, and yeah, you get it. um this is like one of the interesting things about like looking at things like scaling laws or like equations typically assisted with like LLMs or training, is that things are often if you think about things typically, like people like to think about things additively, right? 2 plus 2 plus 2 things that, but like typically we think about like exponentials, in this case like 2 raised to the power 3. um, and logarithm is the inverse of exponent, right? In logarithm, it's like this will log 2 of 8. This is how many times can you like divide 8 by 2 until you get to 1, right? So you continuously divide 8 by 2. So you can do that 3 times, which is again the reverse of this process, right? So if you take the exponent of a log, you get back the number inside, or the log of an exponent, you get back the number inside. So it's like inverting initially. And so a few things to note: log n of n equals to 1, and log n of 1 is basically equal to 0, and n cannot be 1. So if we go over here and look, if you at this graph that Codex nicely like generated for me, this chart, what you typically have is, we have on the y-axis here the uncertainty, or call, which we also call information, measured as like log 2 of like the number of b, log 2 of like n, and so that's in bits, right? So and you have the number of choices. So as the number of choices uh go up, right, by orders of magnitude, what you typically have here is you have the information content growing like linearly, right? So when the choice space is large, information grows logarithmically. Actually, grows logarithmically in terms by base. So it's basically the log of like the total number of choices that you have. So this like goes up to 0, 2, 4, 6, 8, 10. While you have this like growing up greatly. So at like 1024, you have like just like 10 bits. And if you're working with, well, in reality, we don't like using the total number of choices. We typically work with like probabilities instead, because number of choices tells us, given this total number of choices, here is like the information content of a set of the set of choices, right? But we are typically interested in just a single item out of like many items, and so we'd like to like work with probabilities. And so if you think about probability, given like n items, the probability of any single item is 1 over n. And this is like really interesting, because from this you can actually easily derive like the information content of a single item. So let's look at it this way. We know that information is like log 2 of n, and log 2 of n is basically equal to log 2 of 1 over p. That's 1 over the probability of a single item. So why does this hold, right? If you think about it, p is equal to 1 over n. Which is here. 1 over p is basically then 1 divided by 1 over n. That's 1 times n over 1 is equal to n. So this is equal to this. So therefore, log 2 of n equals to log 2 of 1 over p. And if you expand this, what you basically have is, by laws of logarithm, log 2, log the base a over b is equal to log a minus log b. So you have log 2 1 minus log 2 of p. All right. So, and by again the laws of logarithm, log 2 of 1 is basically 0. That gives you minus log 2 of p. If you've been like training machine learning models, you might kind of be familiar with like this looking like a loss function called cross entropy loss, and we're going to get to like how cross entropy loss is actually derived. But like this is basically then means that you could find the information content of any choice set by taking log 2 of the total number of choices, or the negative of the log of the probability of a single choice. And so if you think about it, under a uniform distribution, it holds that both of those are equivalent. So in uniform distribution is a distribution where all outcomes are equally likely. So let's look at this, for example. Given the prefix, the cat sat on D, you could predict maybe mat, sofa, chair, bed, floor, right? Let's say we have like 5 different items, and at each time we get like a unique outcome. So like different, each of these like completions is like equally likely. You can compute the information content or the degree of uncertainty or maybe the surprise of seeing any of these items by doing either the uh, like either doing log 2 or 5, which is choices that gives you 2.32, or negative of the log of 0.2, which is that of like math in this case, which is 1 over 5, or any of these actually 1 over 5. And you see the information is the same. But let's look at a skewed distribution, a distribution that is not uniform. So if there's any skew in your distribution, in this case, you have math occurring twice and sofa occurring twice and share only once. If you compute the information content of maths, is 2 over 5, that's 0.4, negative of the log of that gives you 1.32, versus the log of 5, which gives you 2.32. So in this case, you see that the moment the distribution is no longer uniform, you basically have both of these are not equal, right? So therefore, going further, we are going to be using the negative log of the probability of a single item to measure the information content of that item. So that gives us a view into like the actual information content, the degree of uncertainty of seeing any of the items. Now, one of the things you should also note here is because math only occurs once here, it's it's this all uniform. The entropy, the information content is like higher, it's 2.32. While because it occurs more frequently, so we kind of have a higher expectation. Like we know we are likely to see it. Our uncertainty is less, right? Which also means the information content of seeing it is less. So that 1.32, which is like less than if it's like entirely random. And this brings us to like entropy, which uh extends this concept of information further. And if you've heard about the cross entropy laws or like talk about entropy, we're going to like talk about it here and like really think about like what does entropy mean? What is entropy? When you hear the word entropy, you typically think about the word randomness. But really entropy is not entirely like just random, right? Entropy kind of measures like really like some sort of like average information. And so we're going to like look at this. So information measures the surprise of an outcome, right? So the less likely an outcome is, the higher the information, and vice versa. But entropy measures the like average surprise of our possible outcomes. So if you look at like it's like information measures like, oh, like this is like the surprise of an outcome, and then entropy is kind of like an expectation over information, right? So let's imagine you have a random variable x, which could take on like many different like maybe discrete outputs. um the information content of this can be measured as the summation over the probability of any output. In this case, for example, if you think about this, which we add, right? So like this is like this full set of x, and like each of this is like a single small x. And so the probability of any of them multiplied by the negative of the log of the probability of any of them, which then gives you, of course, the minus summation over the probability of any of them that's the like the log. So information content is like information uh um is like, okay, the average, the surprise, and like entropy is like the average of that, right? And so this was like really established in like great detail by the incredible work of Claude Shannon, mathematical theory of communication. This reading this seminar work was like very helpful for me to like really understand entropy and information in like great detail. And there's a lot of like cool contents from 3 Blue 1 Brown explaining like entropy, which I found really helpful as well. So I've linked some of them here. There's one on like uh compression is intelligence, reverse entropy, and like one on cross entropy, which is also the second part of that series on like compression is intelligence. So I highly recommend like you take a look at it. You can find it on YouTube. So let's look at like an example of like entropy in action, right? So we have that text, so the cuts out on the math, and then you cut out on the, and you have like completion. It can be math or anything. So you got the word, you got the probability, and you got the negative of the log of the probability, and then you have entropy. You can compute the entropy of each of this single item, like each of the single word, and that's like in this case we got 0.2, we got 2.32 as the information content. If you compute the if you multiply those together, you get like 0.46, and so you could basically then compute the entropy of all completions by doing the summation of all of this, right? So you got some days this gives you 2.3 bits. And if you think about a non-uniform distribution, where matter costs twice, so far costs twice, if you do the same thing, you start to see one interesting trend, right? So you see that the entropy, right? If the total entropy, if you like do this and like you compute this, like the total entropy is just 1.52 bits, which is less than the entropy of this. And that's because this is like a uniform distribution, while this is a non-uniform distribution, which basically has like lower entropy because like you there are some items that are like more likely than the others. So this brings us to the facts about entropy. The entropy of a distribution is as high as when it's like uniformly distributed, and any skew in the distribution will reduce the entropy. If you look at the entropy of a single byte, which consists of 8 bits, that's like take 0 and 1, arranged like, it together, like total like 8 of them. And so if you know this is the arrangement that makes sense, then you have 0 bits. If you know that you have like 50-50 arrangements, right, you have like 1 bit, right? Because the p on all the others is basically like zeroed, so they get zeroed out. And so in this case, p, this is the only one that has p of that has a p, and its p is like 1. In this case, there's like this is like 0.5, 0.5, and in this case, you have like 10.5, 0.25 ish. Do you have each one, and then you multiply by the log of the prop. um, and if you continue doing this, what you basically have at the end is uh like the entropy is 8 bits, which is like not surprising, right? In this case, you have like there is like 2 raised by 8 possible ways of arranging like like this like we have 8 bits, right? And each one is like 2, 0, 1. So the more over a totally like uniform bytes distribution, you have like 8 bits as the entropy, and like 0 on the other end. And this fact about information also allows us to like encode data. So this lies at the art of like encryption, lossless versus like yeah, not lossless encryption. And so let's think about like the number of bits that we need to encode data as data, right? So let's imagine we under uniform distribution we have different events up, down, left, right. The probability of this is 0.25 ish, which means they are all equally likely, and so there are 4 of them over 4. And if you compute the information content, you get 2 bits, right? And the entropy is like 0.5, 0.5. One of the cool things here is that, okay, because they are uniform, the optimal way to like send this data, right, is like encode it is with like 0001, 2 bits per a single command here or event, however it's used. And so the entropy in this case is 2 bits. The interesting thing is if you know that the distribution is non-uniform and some event is more likely than the others, for example, up is more be 50% of the time sent, and down is like 25% of the time sent, and we have like lower values for left or right commands. You could exactly compute the optimal prefix code needed to actually like communicate this, to actually like encode this by just simply taking measuring the information content. So in this case, this is 1, so you need just 0. In this case, we have this is 2, you need 1, 0. This is 3, we have 1, we use 1, 1, 0, and 1, 1, 1 for this. And so we can just straightforward compute the exact amount of like bits needed to encode each of these data by just taking negative of the log or the probability of that data occurring. And if you do this and then you compute the entropy, you actually realize that we actually have lower entropy, which is like way more efficient than when they are uniform. So whenever you know some facts about the probability of like how often like your data occurs, you can always use this to reduce the amount of data that you need to like represent things. in this case, we actually increased the amount of data for left and right, but it didn't matter because if you think about it intuitively, the probabilities of us sending them is quite low. So on average, we send them less, and so we use more data for them each time, but it's fine. We only send them a few number of times. But we send up and down a lot more frequently, so we use less data for that. So on average, we overall use less data. And let's get back to like pre-training, right? So we've been talking about entropy, right? So what we really want to do in pre-training is, let's imagine we have this real data distribution, math, so far, share, 0. 0.4, 0. 0.4, 0.2. We want our model to basically have like similar probabilities for them internally. So if we sample the mode output, given that context, if we sample the output like multiple times, we really want the model to like about 40% of the time predict math, about 40% of the time predict so far, 20% of the time predict share, because that's really what happens in our data. So we're trying to like basically let the model have like a same distribution. And cross entropy kind of allows us to like really measure well how this kind of like aligns, like how does the how is the how does the prediction by the model align to the actual data that we know we have? So and going further, we'll be using like natural algorithm, which we measure in NATs for optimization purposes. You basically like use base ease instead of base 2. And in this case, our model will be answered by theta. So let's look at this. You have some context, right? Let's say the sum of 2 and 3 is, that's like your context represented as x less than t. That is all x values below t, which t is the current word we're trying to predict. And then you have the actual next word that happens in the real data, which in this case, let's say is 5. Sum of 2 and 3 is 5. So if we have this in our data, we know the probability of this is 1 because that's exactly what occurred. So we already know. So the distribution there is 1. The capital of the US is Washington. The data probability xt given x less than t. The data is 1. Our u is 1. And so, but if we give this to our model, right? Let's say sum of 2 and 3 is, let's say our model is like really like not that great, and our model if you put x less than t in our model and has to predict xt, it only gives a probability of 0.2 to 5, which is like very low, right? And maybe the capital of the US is, maybe the model gives a higher probability to Washington, 0.8, so that's good. Not perfect, as we would love this to be like 1.0, but like it gives a high number. Our U, maybe the model just like, yeah, it should be like U after our, and so it gives like perfect number, like 1, probability of 1 assigned to the token U. So what we then have here is, we could compute the cross entropy by multiplying the probability under the real data distribution, which is this, by the log of the model distribution, right? So it was the negative of the log, and so yeah, you could put the negative here. So what you have here is 1.6 knots, which is high because our model assigned a low probability to the actual next token. In this particular case, our model assigned a high probability to the actual next token. So the cross entropy in this case is 0.22, which is low with trending good. And if the model predicts exactly the same thing as in the data, we get 0 knots. Like the uncertainty is absolutely 0, the cross entropy is like 0. Like we know, according to the relative to the model to data distribution, the model is doing perfectly fine. So the key thing in cross entropy is, unlike entropy, where both the left side, the probability, the waiting time, as well as the information content negative of the log comes from the same distribution. In cross entropy, we have the waiting time come from another distribution, which is why there's the cross there, and the actual information content coming from like maybe like the model distribution. And so we would love this to go to 0. And if this goes to 0, it means our model is great, ideally. Of course, in reality, what you do is you do this over some training data, and then you kind of evaluate that on a held out data set and see how well does your model generalize, and get to like your generalization loss. So pre-training is quite simple, right? So you have that whole, you have x1, x2, x7, which is like just represents your your input tokens, and then you have your next tokens below here. And this data is like one not encoded, as we explained as well. So earlier, where you have like the context and you're trying to predict this, and then this call in the data looks like this, right? You got, let's say, like 50,000 tokens. Your vocabulary could be like much larger, and the every other thing has like zero probability because we know that's not what happened from the data. And so the actual token, which is like off, gets all the probability, gets all the weights, right? So px3 giving x less than 3 is basically like 1.0 for off, right? And everything else is zero. And we're going to like use this fact soon. So in pre-training, we have this loss, which is like you take some data from some sequence from your pre-training data set, and you it has a length of t, and then you given it's a summation. You do an average over t minus 1. So you think about this is like 8, x1 to x8, and so the actual input is like, the actual positions we have here is t minus 1, right? It's like 7 positions. So you have like over t minus 1, you start from 2, I equals to 2, again I equals to 2, you start from 2, and you do negative of the log of xi given x less than I, right? So that's like x3 given x less than 3, for example. And so you do an average over this over a single sequence. Basically, this is like per token loss, and then this is like per sequence loss, and then you do a per data set loss, typically a per batch over a data set. So we just do an expectation over like a single batch. And we can derive this exact equation very simply from the KL divergence, right? So if you think about it, right, what we are trying to do is minimize the KL divergence between the real data distribution, which we already know from our data set, and the model distribution, which is like the distribution or the model, like what we are training, right? We want pi theta to like be as close as possible to the real data distribution. So what we do is we do the forward KL divergence, right? Probability, which is basically pxt given x less than t, real data. What is for KL divergence from pi theta, which is the model parameterized by theta, xt given x less than t. So, right. So you do, and so this is basically then by a summation over the vocabulary, right? The vocabulary being like at each position, t, right? What's like the distribution over the next token, right? So you then take PVI, which is like go over every single V in the vocabulary. You have VI giving x less than t log probability of VI giving x less than t divided by pi theta. So this is basically weighting term, the data distribution. On the top here you have the data distribution, and below here you have the model distribution. So this is basically the forward KL divergence equation, and you want to like minimize this. And let's remember again that p, for example, p x3 given x less than 3, the vi actually just collapses to like a 1 odd, where a 1 gets like all the probability and the rest is 0. So they will cancel each other out very shortly. So let's look at this. So we have like by loss of logarithm, log a over b equals log a minus log b. So this becomes log p vi x less than t minus log pi theta vi x less than t. And if you expand this out, it will become the summation of p vi giving x less than t multiplied by log p vi x less than t minus this. And what you see here is that this side is our cross entropy. So this way, because this is the data distribution term, and then this is like the model distribution term. So this is our cross entropy, right? And then you have this is a constant term. Now, why is this a constant term? Because what we're optimizing is only on this side is theta, right? In this case, so this is where the theta is, which is the parameters we are trying to find. If we find really great parameters, then we'll minimize it. So that basically means, because this part is constant because there's no theta here, minimizing this full equation, computing the argument of that KL divergence is basically exactly the same as minimizing just this part. So henceforth, we are going to cancel this out as a constant, and so we're going to have just this, where summation over the vocabulary, probability of vi x less than t from the data, and then we have the from the model distribution, so it gives us the cross entropy. And we know that at I equals to xt, this is 1. At every other position, this is 0. So a summation, the summation then cancels out every other token except xt. And so this becomes the the summation is out. And so we have minus 1 multiplied by log, where this becomes 1. So that's minus 1 multiplied by log probability that the model assigns to the next token from our data. And so the cross entropy loss is just, we can consider that 1 is a constant. So we have just negative of the log of the model's probability, which is typically like uh, negative of the log prop of the model. And cross-entropy laws can be implemented very simply in PyTorch by just, in this case, for example, let's take all tokens up onto T. You could take the input tokens as every token before the last token, that is, and then that's from 0 to like T minus 1. And then you could take the label as the tokens immediately after those, which is like from the second token up onto the last, right? So the predicted logits, you could just pass the input tokens to your model, get the logits, and then compute the log softmax, where softmax turns into probabilities, and then you compute the log of that. And what you then do is, in this case, we have like batch size by the T minus 1 over the vocabulary. Let's remember we are only interested in the actual next token because all the others didn't occur in the data. So the P, this, to do this, what we typically just do is do a touch.gather where we put in this predicted log probabilities, and at the last position, which is the vocabulary position, we just retrieve only the actual next tokens from the data, and this gives us the token log props that the model assigned to the actual next token, and we do a mean over that, and so that gives us like the, and with the negative, so that gives us the cross entropy loss. Supervised fine-tuning is like very similar to this, with a simple difference that instead of just like very large documents on the internet, what you actually have is like, you have like prompts like "How are you?" and you just have like "I'm fine." What's capital France, Paris. So this is like what teaches the model to like be chatty, and so the difference is the way we really arrange the data, and we introduce like some masking. So where at the top we have like the query, and we have the this, and we have xt, x less than t, and xt is just as we had in pre-training. But the difference is we have a mask, right? Where every position that is prompt is zeroed out, and every position that is not the prompt, which is like the model, the generated, the actual answer, we have 1 on that. So what this then gives us is, in pre-training we have minus log pi theta xt giving x less than t, and we just multiply that by the mask, right? In where the mask is 1 if the token is greater than the prompt length, or 0 otherwise. And SFT can be implemented exactly similar way. We just like have an additional mask, and we basically just pick that mask up onto the first position above. We do everything as we did earlier and just multiply by the mask. One key thing here that's like trip your implementation: if you just do a main like we did earlier, that's not going to work, because you'll be doing a main over like this entire position, while with the 0 mask, once you multiply by 0, this is really the only part that's active. So you need to multiply by the sum of the mask. 1 plus 1 plus 1 plus 1, that's like 4 instead of like 7 here. Right, so in order to get that 4 instead of 7, what we do is mask the sum and clamp it to 1 to divide by division by 7. So that gives us our SFT loss. RL is like interesting because in RL, the main difference is we do not take like some prompts and answer data sets. We take some prompts, and then we generate, for each prompt we generate the answer from the model we are training itself, which is why it's called on policy, because at each single step the answer we're optimizing on is actually generated by the model we are training, right? So it comes from the model's own distribution. So what we are really trying to do is optimize the model such that it generates answers from that like when it generates answers that are good, we want to encourage that. When it generates answers that are bad, we want to discourage that, versus like just like giving it some gold answer and like thing like the SFT loss on its pretraining loss. So one way to think about it is um pre-training is like someone is just like reading a book, and RL is like you're actually doing practice, like maybe you are doing some working out some maths and coming up and you're learning from your own successes and failures, right? So RL is really learning from data you generate from by yourself, right? And you learn good things from, you learn to like generate more of the good data and learn to generate less of the bad data. So let's say, for example, we do what is 3 by 4 and the model says 10 as wrong. And we compute what we call an advantage, which in a naive sense could be something as simple as just like, the playing reward or like computing some sort of like baseline reward and doing like subtracting that from the reward for each one. So let's just think about it this way as like we have -1 for this, we have +1 for this was good, and we have -1 for this. Uh, RL loss is like very simple because what it simply does is we generate some data in an online manner, we assign some reward, and instead of this SFT loss, we simply replace this one. Remember, pre-training loss is really just -1 multiplied by this because 1 for the actual next token. And SFT loss extends that RL is basically replacing this 1 by disadvantage, right? So, which is basically saying when we did something bad, we get like maybe -1 here, like lower the probability of this like token on action. And when we do something good, we get +1, which is like encouraged. So we really want to just like encourage. This is like called policy gradients. I really want to like encourage good behaviors and discourage bad ones. So the RL algorithm is like really simple. Like select prompt X from the data set, generate a full response Y from the model condition on the prompt, score the response, right? Evaluate Y with like a verify or reward function, and then we can just like distribute that response, that the advantage across the individual tokens, right? So even though each single rollout is like a full sequence, and we compute just one single number of them, like as a add like how good or bad, we can then uniformly distribute that number over like every token that is sequence. That has its problems, and we are going to talk about that soon. So you then compute the loss as like mass multiplied by the assigned advantage times the log probability of the token. You can read more on like this is kind of like some variants of like reinforce, which is run by Ronald Williams. I've linked the paper. You can search for this paper and like read it. So area loss is similar. What we do is we have some rollouts, we have some mask, and we have advantages, which tell us how good it is. So, um, in this case, your advantage, yeah, in this case, will be like just one part the by a single sequence in your batch. And so what we have is you have the rollout, which again you pick the input IDs as like the rollout up until like almost the last token, and then you have the label, which is like first token upwards, and the label mask is like similar to the label. You compute the logits, you take the log prop of that, and then you pick the position, you pick the label positions, and what you then do is you multiply by the mask, just like we do in SFT, and you also multiply by the advantage. And this gives you like a B by T minus 1 size. And you do a sequence loss again by dividing by the by the mass sum. Like you do a sequence loss like over the each rollout, right? And then like you divide by the mass sum, and then once you've got per sequence, you then do a main over that to get like the patch loss. So this is basically the RLOS. And but there's a bit of an issue with this, which let's say is like PPO style algorithms. And one of the issues is that once you generate a rollout, it can be like a very expensive rollout. So if you, for example, your training and your agent, part of your training is like your agent will go to do some work for days. You kind of like want to like learn repeatedly on that data if you can, for like sample efficiency, so like you don't waste a lot of compute. And so what you really do is you want to take multiple optimization steps over every single sample. But the problem is if you naively do that, the moment you take the very first optimization step, the next optimization step is kind of like off policy because the policy has changed, and now you'll be taking optimization steps on like data generated by an old policy, right? So we have the once you each the at each new step that you are iterating, you have what we call the new policy, and then you have the old policy, which is the policy that generated the trajectory. And so what you typically do, like in like PPO, is you do like a mass by you multiply not by just the log prop but by the ratio of the log prop in the new policy divided by the log prop in the old policy. um and this there are other things to PPO, but this is like really I think the part that's kind of like survived a lot till today, especially with like algorithms like GRP and rest. So this is like kind of the really the central part of it. And so if you think about this, one way that you could, because in ML optimization we typically don't like division. So one way you can really like just express this is you could turn this into a subtraction with a very simple and clever approach by doing that. This is equal to the exponent of the log of this. And why is it equal? Because exponent of the log is like saying 1 multiplied by, because it's exponent and log invert each other, so this is basically equivalent. And so once you have the log there, what then this allows you to do is log a over b equals log a minus log b. So you have exponent of the log of this minus the log of this. So exponent, so you have what we call the PPO ratio, which is the exponent of the log prop under the new distribution minus the log prop under the old distribution that generated the data. And so PP also includes an additional clipping where you have the unclipped loss as like the advantage multiplied by the ratio, and then you have the disadvantage, the advantage that we add, disadvantage multiplied by this ratio, right? And then you have the clip loss as the advantage multiplied by a clamp of the ratio from like you clamp the ratio from like 1 minus e to 1 plus e, and then you can do the loss as like basically just the minimum between like these two, right? So you don't want your policy to like drift too much, and then you have this e to like kind of like control for the of policiness, and then you can't like take the mean of this one, right? So let's look at this. So what is, then you have like GRPO, which is like a variance of PPO that replaces the value function with like a groupment. And so like a subtraction from a groupment. So you have like, you can sample, given a single prompt, you sample like G rollouts, and then you can evaluate each rollout with a verifier or some reward function. You compute the mean of this, and then you can compute the advantage as Ri minus U, and like uniformly distribute this over like each sequence. Note that this that I'm showing is a modified version of the original GRPO, which is like, which the original GRPO included like a normalization by dividing by the standard deviation, but that encourages some bad behavior sometimes in terms of reasoning models, and so this has been shown to like work just as well without like a number of issues. And so the GRPO, you can implement like GRPO be like this, and it's like quite simple, right? You have so on the right here we have a function to like get log prop of giving like some labels and some inputs, and so you have everything we did previously, and what you then do is you get the old token log prop, which is like what from like the what we generated, the policy that generated the trajectory, and over a range of what we call PP epochs, which can be like 4 to like maybe 5 marks. You have like at the very first position, the new token log prop is the same as the old log prop, right? So while for the optimization steps, the new token log prop is you need to like rescore the trajectory under the like new policy. And so what you do is compute the ratio by doing an touch dot exponent, new log prop minus old log prop, and you detach from the old log prop because we are not trying to back propagate through the old one. And so you do the unclipped is ratio by advantage, the clipped is the touch dot clamp multiplied by the advantage, and then you take the minimum of those two and multiply by the label mask, and you do your sequence mean and like your batch mean, and you can update your model and do this over and above epochs. So this is basically the GRPO code implementation. It's like quite simple and like very elegant and like works. One of the big problems with RL, and you might already be saying that, is like we computing the advantage, and like once per sequence, like, okay, this is how good this sequence with a single number and we are spreading it over action. So it doesn't really tell us what token actually is bad, right? A trajectory could contain like thousands of tokens, right? It's like what token is like bad in that trade, which tokens are bad, which ones are good, right? And so in order to estimate that, what we really do is like do a lot of rollouts, which enables you to reduce like the variance. And this is like GRPO's approach, and that's like enables you to like estimate like the what works and what doesn't work, but it's kind of like very inefficient. On policy distillation, first like popularized by the Rishab Agawal from Google DeepMind, and then thinking machines recently like you know made this like very popular towards the end of last year with the on policy distillation blog post that they did. And what this really does is just enable the model to kind of like learn from like a very dense credit. And what that really means is you use some sort of like teacher, which could be the model itself with some feedback, or it could be a larger model typically to like train another model. So that allows you to kind of like get like an advantage per token rather than just per sequence. And we're going to look at exactly how that works. So reverse scale formulation is like what we use here. We measure like what we call like the reverse scale divergence between like the student and the teacher, where the student is the model we are training and the teacher is maybe a larger model, right? So that could be like a much larger model which we want to use to like supervise the students, or it could be the student itself with some extra signal. So let's say we have a number of prompts x1 to x3, you sample responses x4 to x9 using the student model by theta. So that gives you a full trajectory x4 to like x1 to like x9. What you then do is you compute the token log probabilities, the log probability tokens under the student's model. So which is like basically this step, right? This step that we do. You compute that under the student model, and then giving using exactly the same trajectory that the student generated, that exact trajectory, you use that, you score it under the teacher, right? And so it's then you want to minimize the reverse scale between what the distribution under the student and that of the teacher. And so one way you can do this is using reverse scale, where you do probability of student multiplied by the log of the probability of the student divided by the probability of the teacher, and of course by laws of logarithms. This becomes the log p student multiplied by log p student minus log p teacher. And so what we really want to minimize is like this, right? This part, right? We want to minimize this. So in RL training, we are trying to maximize the reward, so we can like maximize this by like by like just like computing the reward by taking the negative of this, right? So if you take the negative of this, right, that gives you like, oh, you want to maximize what you should maximize. So that's very neatly ends up giving us the log prop of the teacher minus log prop of the student, which makes the reverse scale loss extremely simple, because you just need to compute the log prop under the teacher and the student and like do a subtraction. Let's talk about the student trajectory where the square root of 647. Of course, this is what is wrong, but that GRPO, like we just like assign our this is all bad, right? But this is really what's bad. And so let's imagine the student's probe is like 0 0.9, 0 0.9, 0 0.6, 0 0.95, 0 0.8, 0 0.7. For this token, right? This token is supposed to be like really low, but like the teacher, the students are assigning high probability to it. So the teacher might, let's say the teacher is really good, assign 0.8 to this, 0.9, 0.75 to this, 0.9, 0.65 to this, and 0.1 to this, because the teacher, assigns low probability to the incorrect token. So what we just do is just do a subtraction over this, and what we end up with is very highly negative reward on 7, which is great what we want, and much lower values on the rest, right? Very low negative on this, 0 on this, because it's exactly the same to low negative, low negative. So that's not really the problem. This is the problem, and we know that intuitively from doing this. And on policy distillation is like very simple enough, comparable to like in terms of like implementation. what we do is we have input IDs, we label IDs. We don't have an advantage, we compute the advantage here. And so we have the label mask. Again, we want to still mask out our prompts. We only want to optimize our model's output. So we have a student model, and we take the logics there. We compute the log prop, and then we pick the actual probabilities of the actual, like tokens that the model generated, like the most likely tokens, like its sequence. And what we then do is we do touch.nograd, because again we don't care about the gradients from the teacher, we only care about using it to compute an advantage. And we do exactly the same things, called the trajectories, called the actual next token that the student generated under the teacher. And so we do advantage being the teacher tokens minus student tokens, and we detach this because the advantage, we are not trying to backpropagate to the teacher once, and like there's no reason why we should have the gradients flowing through this, so we just use this to compute a reward. Think about in RL, your advantage would typically be a non-differentiable function anyway, so you do it detach it. And the token loss is then negative of the student log prop multiplied by the label times the advantage. Again, this then boils down to exactly the same thing, with just this relay being how we compute the advantage is really different between policy distillation and standard RL. And so this allows us to, with much extreme efficiency, compute, like train large language models, as long as you have like a good teacher that you can like learn from, which is like way more efficient than using like standard RL. But this has its limitations because the student's context could bias the teacher trajectory. It's not perfect. And also the student, you can't expand beyond the distribution of the student. So you can't really like, like, because reverse scale is mode seeking, if the student never samples the trajectory, it never learns from it. Because you're sampling from the students. And you can mitigate this using like either using Ford KL as an additional signal in some ways, or using large scale SFT to like distill maybe the knowledge of the teacher into the students before then doing RL. But there are different ways that you could do this, and like it like it's all like works like really fine. So that is really the end of this video. I thought about doing the code. I have like code implementation for all of this, and wanted to like trade, but I thought that was gonna like need like at least about a 30 minutes video of its own, because yeah, there's like really interesting things to walk through and like really, like see how this actually trains in practice on like example tasks on like reasoning and all of that. So I'm gonna be making another video on like a code implementation of on policy destination as well as GRPO. But in the meantime, this way I'm gonna stop this video. Thanks a lot for listening. And like it was really fun like putting this together. Subscribe to this channel if you want to like see more videos like this, and feel free to like reach out in the comment section with like any questions like you have on this. And yeah, in the meantime, have a great day. Thank you for listening to this video.